Welcome to today's topic on the action of alkalis on certain metals and their oxides. Now, have you ever wondered how metals like zinc, lead, and aluminum react with strong alkalis such as sodium hydroxide or potassium hydroxide? Well, these reactions not only produce salts but also release hydrogen gas. It's quite fascinating when you think about how these seemingly simple reactions happen right in front of our eyes. Let's dive into the chemistry behind it. When alkalis like sodium hydroxide or potassium hydroxide react with metals such as zinc, they form salts. These salts are soluble, meaning they dissolve in water. And the byproduct? Hydrogen gas, which is released in the reaction, just like when zinc reacts with hydrochloric acid. This release of hydrogen gas is a classic demonstration of a redox reaction where zinc undergoes oxidation, losing electrons while the alkali is reduced. Isn't it amazing how simple chemicals create these reactions? Let's look at some specific examples. Take zinc, for instance. When zinc reacts with sodium hydroxide, it forms sodium zincate, which is sodium to zinc to oxide, and releases hydrogen gas. You can picture this happening in a test tube where the reaction produces bubbles of hydrogen gas and the solution turns into a clear, colorless liquid. Similarly, when zinc reacts with potassium hydroxide, it forms potassium zincate, which is potassium to zinc to oxide, again releasing hydrogen gas. Moving on to lead, when it reacts with sodium hydroxide, it forms sodium plumbite, which is sodium to lead to oxide, along with hydrogen gas. Interestingly, lead does the same with potassium hydroxide, but it forms potassium plumbite, which is potassium to lead to oxide. And the gas released? You guessed it, hydrogen gas. Finally, let's talk about aluminum. Now, let's take it a step further and explore the reaction of alkalis with oxides and hydroxides of these metals. Oxides and hydroxides like zinc oxide, lead oxide, and aluminum oxide are amphoteric, meaning they can act as both acids and bases. This unique characteristic allows them to react with both acids and alkalis. For instance, when zinc oxide reacts with sodium hydroxide, it forms sodium zincate, which is sodium to zinc to oxide, and water. Similarly, lead oxide reacts with sodium hydroxide to form sodium plumbite, which is sodium to lead to oxide, and water. These reactions help demonstrate the amphoteric nature of zinc and lead oxides. In the case of aluminum oxide, when it reacts with sodium hydroxide, it forms sodium aluminate, which is sodium to aluminum oxide, and water. This amphoteric behavior is vital in various chemical processes, including the extraction of metals and the treatment of industrial waste. Moving on, let's examine how alkalis react with the hydroxides of these metals. For example, when zinc hydroxide reacts with sodium hydroxide, it forms sodium zincate, which is sodium to zinc to oxide, and water. Lead hydroxide behaves similarly, reacting with sodium hydroxide to form sodium plumbite, which is sodium to lead to oxide, and water. The same goes for aluminum hydroxide, which reacts with sodium hydroxide to form sodium aluminate, which is sodium to aluminum oxide, and water. This pattern of reactions further emphasizes the amphoteric nature of these metals. Zinc, lead, and aluminum hydroxides can act as acids or bases, making them very versatile in chemical reactions. Now, let's connect these reactions to the real world. The reaction of zinc with alkalis is important in the industrial production of various salts which are used in many industries, from manufacturing to pharmaceuticals. For instance, sodium zincate produced in this reaction is used in several applications, including the production of batteries. When aluminum reacts with alkalis, it leads to the formation of sodium aluminate, which is an important compound in the production of detergents and soaps. In fact, the process of producing aluminum-based compounds is crucial in many chemical industries. The action of alkalis on metals and their oxides is not just an academic exercise, it's a key process in a variety of real-life industrial applications. Let's now work through a numerical example to reinforce our understanding. Imagine you're given 10 grams of zinc and asked to calculate the amount of hydrogen gas released when it reacts with sodium hydroxide. The reaction is zinc plus to sodium hydroxide gives sodium to zinc to oxide plus hydrogen gas. Now, the molar mass of zinc is 65.38 grams per mole. First, calculate the number of moles of zinc. Moles of zinc equals mass of zinc divided by molar mass of zinc. This gives you the number of moles of zinc that will react with sodium hydroxide. Then, based on the stoichiometric ratio in the balanced equation, you can calculate the volume of hydrogen gas released at standard temperature and pressure. Remember, 1 mole of gas occupies 22.4 liters at STP. Using this, you'll be able to find the volume of hydrogen gas released. This example brings the theoretical reactions to life and shows how we apply stoichiometry to real-world chemical calculations. So, to sum up, we've learned how alkalis react with metals like zinc, lead, and aluminum to produce soluble salts and release hydrogen gas. These reactions highlight the importance of alkalis in chemistry and their role in the formation of useful compounds. We've also explored how alkalis interact with oxides and hydroxides, emphasizing the amphoteric nature of these metals. These reactions are crucial not only in laboratories but also in industries where metals and alkalis are used to create products ranging from detergents to batteries. I hope this session helped you understand how these reactions work and why they're so important in everyday life. Catch you in the next class where we'll explore even more fascinating chemical reactions.